Hi everyone, I welcome you all in the second lecture of quantum mechanics. So in previous lecture we have already talked about the state and state space of quantum mechanical system, as well as I have also described some fundamentals regarding linear algebra. That concept can be further translated to the quantum mechanics as well. So in today's lecture, I will be talking about the operator. That is very important concept. And like in classical physics, what happens? Let's say if we have to describe the let's say linear momentum or angular momentum or kinetic energy, then you will be having some numerical value for that, and you can exactly calculate, or you can exactly tell what is the linear momentum, what is the kinetic energy and potential energy of the particle. But here in the quantum mechanics, basically what happens, we use an operator to describe these kind of observables, that is the measurable properties in the quantum mechanics for the particle. Let's say if you want to calculate the kinetic energy or linear momentum or position of the particle, then you have to indicate this, or you have to import this using the wave function, operator. So operators are very important. So first we need to understand what is the definition of the operator. So the definition of operator can be, the operator can be described as it's just a mathematical expression that you apply over a function, and that function gives you another function, right? So how this works? So let's say you have an operator A, right? So if you select an operator A, and if you select a wave function or psi, if we select a wave function psi, and this operator will operate over a psi, let's say this operator will operate over a psi, and that will give you the same value of the function, but a measurable property. Let's say this one is A. So A, I will call it as observable. A will be your observable. A is your operator, and this is your, let's say here is a wave function, or here I'll just assume this is a function. And it will give you the same function. It's very important to understand here. So this operator is operating over a function that is giving you a particular value, and this will be the observable. That means the value of this observable you want to measure using this wave function or function, and then again it will give you a function. So if you see these things, it looks like the eigenvalue problem. This looks like an eigenvalue problem. In eigenvalue problem, basically what we do, so you have an operator which is acting on a function, and that gives you the value here that you can see observable, that will be called as the eigenvalue, and this function will be called as the eigenfunction, right? So this is also called as the eigenvalue. And this function is also called as the eigenfunction in quantum mechanics, or sorry, in mathematics. Is that clear? So this is how eigenvalue problem, that is the concept of linear algebra, that can be used here in the quantum mechanics, right? So that's important. So we get to know what is the operator, and because here you can see that this function is getting translated in another function, and then you are getting a measurable quantity, something like that. So now we are going to use this concept in quantum mechanics, and we'll try to calculate some fundamental physical properties of wave function, right? So first I'll start. There are various kind of operator in quantum mechanics. So first I'll like the positional operator, linear momentum operator, kinetic energy operator, and potential energy operator, total energy operator, that is Hamiltonian, right? So I'll start with the position operator. So basically it is denoted as capital X. So when we talk about position operator, so again there is a wave function psi, right? So I am assuming this is a function of x. So this position operator will basically operate over a wave function psi, and that will give you a value of measurable properties. And here, since the operator is a position operator, so the measurable property will be the position of the particle, and this will give you a function of psi, right? So this is your position operator. And this is your wave function, and this will be this is your position of the particle. And again this is your wave function. So you can see here how this position operator is being operated over a wave function side, that is giving you a position of the particle and that same wave function. And this is also a eigenvalue problem. So in this case you can see that position will be your eigenvalue. This position will be your eigenvalue. Now coming to the next operator, that is your linear momentum operator. So it has been denoted as capital P. Right? You can denote it as capital P. So basically what happens, if this operator will operate over a wave function, that should yield you linear momentum and then this thing. So let's say if you have a wave function psi, so this linear momentum operator will operate over a, this linear momentum operator will operate over a wave function psi, and that should give you the linear momentum of the particle and this side. Again, this is eigenvalue problem. If you see here, this is your function, this is your operator, so this is your and this is your linear momentum of the particle. That is the measurable property you want to calculate. Right. So if you see the linear momentum operator, the value of linear momentum operator, that is equal to minus I divided by h del by del x. Sorry, minus IH. This is minus IH del by del x. So basically what happens here, so you have a wave function, let's say psi, and then you operate this linear momentum operator, so that is your minus IH del psi by del x, that will give you a value of linear momentum P naught, and this should be psi. So basically how these things can be calculated, it's very important. So let's say we assume a wave function psi that is equals to 1 upon root 2 pi h and e to the power minus I by h P naught. So when we talk about this wave function, that is called as the pure state of linear momentum. Right. So if I'll differentiate this wave function, let's say if I'll do del psi by del x, just try to find what you will get here. So it will be equals to minus I by h and 1 upon root 2 pi h e to the power minus I by h P naught x, and then you will be getting the value of P naught.
One note, there is not psi.
Oh, sorry. So this is not psi. This is your P operator. Right. So this is P operator. Now, once you get this thing, now let's try to multiply this equation. Let's say if I assume this equation is 1, if I multiply both sides by I into h, right, in this equation, so I'll have minus I h del psi by del h, that is equals to I square minus minus, it will be plus and it will get cancelled out, and finally it will be P naught into 1 upon root 2 pi h e to the power minus I by h P naught x. Is that clear? So if you see this value, what is this value? This value is the wave function that we have assumed here. Right? This is your pure state of wave function for linear momentum. So this is your psi, overall wave function. So basically what we got here, if you see here, then we have what? Minus I x del psi by del x right? So that is equals to your P naught into psi, because this was the wave function that we have assumed here.
Actually, one more problem here. Okay, when I multiply with minus iota into h in both side, then it will give the minus p naught, no?
No,
This
minus
is
is there, no also. I
but I will multiply with the minus iota ih, no? Can you separately calculate it?
So let's say if you calculate minus, then iota h divided by h, and then sorry, this is minus iota by h, and then you start with minus ih.
Yeah.
Minus minus plus, that is minus. So there will be a minus here, right? That is minus iota h. If you do multiply with positive, so that will be minus. This side it will be minus. Yeah. So anyway, you will get negative sign over here.
Yeah.
Ultimately, you will be getting a negative sign because of this I square term, right? So ultimately, you are going to get the minus IH del psi by del x only, right? Ultimately, if you are multiplying with the so you try to multiply with IH, only IH, right? So you will be getting the negative sign here. So now, very important thing to understand here. So if you see this wave function, so I can write this as like minus IH del by del x psi, that is equals to P naught over psi. Is that clear? So ultimately what you can see here, that this operator is operating a wave function, it is giving you some measurable properties, and then this is a psi. So this operator is called as the linear momentum operator, which is operating over a wave function psi, that is giving you a value of P naught, and that is the value of psi. Right. So this is how you can calculate the linear momentum operator, from the wave function using this wave function. And this wave function is the pure state of otherwise. No, so the wave function should be like capital IV by H. If you will see, it should be positive I by H. Is that clear?
Yeah, improve at all the places. Improve please all the places. Plus iota.
So if it will be a positive value, then if you do differentiation, you will be getting like that. So you will be multiplying with the plus IH both sides, and then you will be getting the same expression. So expression will not change as it is. It will be as it is. Only if you take this positive value, this will be the side. So here it will be positive I by H. Something like that.
Actually, after the differentiation, we get the plus iota by h.
Yes.
So please modify.
No. So once you differentiate these things, you will be getting plus iota by H.
Yeah.
Right. So if plus iota by H, then you are multiplying with the IH, iota into H. Then it will be negative side in the left hand side, and it will be positive. And that you have assumed this wave function. Again, the expression will be same as it is.
Okay.
Right. So earlier the wave function was wrong. That's why you were confused about these things. Otherwise now the things are right. Stop.